Alright, so this is a very classic and fun example. What we have here is a jet, which is flying on a path with a given speed v, and we're told that at position A on the loop the speed is a given numerical value, the magnitude of acceleration is a given numerical value, and the tangential component of acceleration is a given numerical value. And what we're asked to find is the radius of curvature of the path of the jet at this instant. Well, there's a lot of terms here that kind of give us a hint of what coordinate set we may want to use, but I think probably the key thing is really simply the path. And so you might expect we want to use path coordinates, and that's indeed going to be the case. So if we want to use path coordinates, it might be helpful to define a vector set. So we'll have our tangent and normal coordinates defined as such. And we can recall at this juncture that the acceleration in terms of the path coordinates are given by v dot, the rate of change of speed, in the e sub t direction, plus in this case the speed of the jet squared divided by the radius of curvature in the e sub n direction. Now in this case, we could also rewrite this in terms of a given in the problem, which is the tangential acceleration, and so I'll simply choose to re-express this as a sub t in the e sub t direction, plus v squared over rho in the e sub n. Now in this case, I'm not given the acceleration exactly, but rather the magnitude of acceleration, and so I'm going to convert this vector expression into a scalar one by taking the magnitude. And so if I do that, I'll have that the magnitude of a squared will equal a sub t squared plus v to the fourth divided by rho squared. Now at this juncture, it proves prudent to do a little bit of mathematical manipulation. And so if I do that, what I'm going to find is that rho, the radius of curvature of the path, is going to equal the square root of the speed squared divided by the magnitude of acceleration at that instant squared minus the tangent acceleration quantity squared. In this problem, you're given numerical values for v, the magnitude of acceleration, and a sub t, so you can find the radius of curvature of the path. Given that doing so is purely numerical, I'll leave it up to you to do. Best of luck.